again, I'd like to remind everyone that the purpose of us learning the kinetic theory of gases is to understand the macroscopic properties of gas such as pressure, volume, and temperature. We're going to understand it in terms of the atomic or molecular properties and behavior, which involve the maybe the particle's speed or the particle's energy. Okay, so temperature just now, as you mentioned, is a degree of hotness or coldness of the gas. But if you choose to relate it to the atomic or molecular properties and behavior, we know that the higher the temperature of the gas system, that means by the gas molecules inside should be moving more vigorously. They should be more excited because they have a lot of energy, internal energy, so it causes it to move faster. Okay, so because of that, if we think about it in terms of the microscopic behavior of the gas molecule, we can relate the temperature here to the speed of the gas molecules. That means we can sort of imagine that if you have higher temperature, the gas molecule should be moving faster in general. Okay, if the temperature is low, then probably the gas molecules will move more slowly. Okay, so this is what we can do. We can try to relate conceptually by using our imagination, that we can relate these macroscopic properties here to the microscopic behavior of the gas molecule. Okay, for pressure, we know that pressure is related to the gas molecules hitting on the wall, right? So this pressure here is a macroscopic quantity, but I can relate it to the collision of the gas molecules with the container. So later, we'll spend a great amount of time trying to study how does the collision of gas molecules with the container result in pressure. So we'll be able to relate later the collision with the pressure, which will spend quite a long time to do so. Okay, this temperature is easy to relate, but pressure is the one that takes a bit more time. Okay, so to understand all this relation between temperature, the microscopic properties, and also the speed, which is the microscopic behavior, we need to define a model in which we study the gas. Okay, so what kind of assumption are we going to make for our gas? So to do that, I'm going to introduce to you the model that we are using to analyze our gas. So we are going to analyze our gas as an ideal gas based on the kinetic molecular model. Okay, so there's a few assumptions that we are going to make for our system over here in order to be able to analyze it simply. Okay, if we don't use this assumption, then to analyze the microscopic behavior will be very difficult. That's why we apply this assumption in order to make the analysis of the gas molecules behavior more doable. Okay, so there are a list of assumptions. I'm going to show it one by one. First, all gases are made of identical atoms and molecules. So we are usually imagining a homogeneous kind of gas. So we are not going to mix up the gas molecules inside. It will be usually made of one type of gas molecules only. Okay, next, all atoms or molecules are constantly moving randomly, colliding each other and with the walls of the container. Okay, so as you can see here, I've already sketched the diagram in which you can see all particles here are moving in different directions. Okay, and the direction is actually random. Some particles will be moving to the left, some particles will be moving to the right. It's totally random. Okay, so when the particles are moving around, what they will do is they'll be colliding with other particles that are also moving around, or they can collide with the wall of the container as well. Okay, so when we see random over here, we are actually specifying the direction to be random and the speed in which they are moving to be random. Some might be moving fast, some might be moving slow, but we know that if we choose to take some kind of average, we'll get a certain value. Okay, the third assumption that we're going to make is that all collisions are perfectly elastic collision. Okay, so this will relate more to the physics that you have learned regarding linear momentum. So if you have a perfectly elastic collision, you see that all these collisions between the gas molecules, all the collisions between the gas molecules and the wall, to have its momentum being conserved. At the same time, it also has its kinetic energy being conserved. That's the core, that's the definition of perfectly elastic collision. The momentum will have to be conserved for the collision, and also the kinetic energy needs to be conserved. So later we'll try to apply this concept over here to study how the molecules hit onto the wall. Okay, the fourth assumption that we're going to make is that the volume of the atoms or molecules is negligible when compared to the volume occupied by the gas. So the volume occupied by the gas is this whole big rectangle over here. And what this sentence tries to say here is that these gas molecules, right, we should assume these gas molecules to be very small little entities. Okay, so their volume of this small gas molecule here is very small. I mean, the volume of the the gas molecules, the volume, the space occupied by one single gas molecule, the volume is very small compared to the whole gas systems in which the molecule is being situated inside. Okay, so we can assume all the gas molecules here to be something extremely small in terms of size when compared to the size of the gas container. Okay, next one, the intermolecular forces are negligible except during the collision. So intermolecular forces, there are many types that we learn in chemistry. You learn about dipole-dipole, you learn about London forces. So all these kind of forces are forces that act between molecules. You have one hydrogen molecule and another hydrogen molecule. Probably they have some interaction with each other, causing them to attract or repel each other. But for this study, based on the kinetic molecular model, we are going to neglect all these kind of intermolecular forces. So we are assuming that all these molecules inside the system here, they are not trying to attract each other using London dispersion forces or through dipole-dipole. They are not attracting each other, they are not repelling each other. They're just moving in their own independent way, unless they happen to hit on another person, then hit on another molecules, then they will change direction or change speed. But without that, we assume that there's no one molecule trying to attract another molecule because there's no intermolecular forces in play. Okay? The last assumption that we are going to say is that the duration of collision is negligible compared with the time spent traveling between collision. So you can see that if a molecule happens to be moving, the amount of time that it is moving in the gas system will be much greater than the amount of time that it takes to collide and change its direction. So the motion takes a lot of time, but the collision only takes a little bit of time. The collision only happens for a very small duration only. So we can say the duration is almost negligible if you compare to the time it takes for you to reach the wall and leave the wall. Okay, so duration is negligible for the collision. So these are the few assumptions that we take for kinetic molecular model. So once you understand these few assumptions, later we'll apply these assumptions over here to derive an equation that relates between the pressure and also the speed of the gas molecule. Okay, so for now, this is kinetic theory of gases.